Hello and welcome to the module 4 part A. In this lecture we are going to address multilayer perceptron. In this lecture first we introduce multilayer perceptron and we try to understand why MLP is required over singular perceptron. Then we discussed various components of multilayer perceptron. We focus on these activation functions, and then we define what we mean by feed-forward neural network. Then we try to understand the expressiveness of the multilayer perceptron, and we conclude by saying the applications of multilayer perceptron. As we have seen in the last class, that there is some limitation of single-layer perceptron, that this single-layer perceptron can only solve the problems that are linearly separable. So there is some linear type of separator. In this two-dimensional case is a straight line or a linear hyperplane that can separate these data points. And for these linearly separable cases, the SLP can model this problem. But it cannot solve the problem where these data points are not linearly separable. In this diagram you can understand the data distribution is such that there is no linear separator, only straight line in this case is available that separate out these two points. So this kind of problem this single layer perceptron cannot handle. Okay, so now for example we have seen that AND gate or OR gate can be modeled by singular perceptron, but the XOR gate it cannot model. So you can see in the XOR gate that there will be no single straight line that can separate these two data points. Okay, to solve or to mitigate this problem, we introduce another perceptron that is called multi-layer perceptron. The multi-layer perceptron means that there is more than one layer. Thus, in single layer perceptron, there is only single layer, only one layer. But in multi-layer perceptron, between input layer and this output layer is another layer. It is called hidden layer. Now, see, this is the XOR problem, and this XOR problem that we know this is the truth table 0, 0, 0, 1, 1, 1, 0, 1 and 1, 1, 0, something like that. Now, if we plot it, it looks like this, and since it is clearly understandable that this problem is not linearly separable. Now, question is how this multi-layer perceptron, the perceptron which has an extra layer in between input and output, solve this. Now, this H1, this is the neuron in hidden layer, is basically defined something this logic that not x1 plus x2, that means x2 and not x1. So if both are this, that it is 1, and H2 is basically x1 and you say x1 and not x2. So this is the H1 and H2 that is defined in this, and you can see this thing, this AND gate and even NOT gate, this can easily be implemented by a single layer perceptron. Okay, so initially this is the single layer perceptron and this is the single layer perceptron, but this extra layer going to use these two. Okay, now if we can see that if either this or this combination both are ones, but if these two combination are not going to hold, then this is 0. Okay, so in just what we are going to do, that our Y, the XOR gate, is basically that H1 or H2. So this is our logic, and it's again a single layer perceptron. Okay, so just putting another layer in between, we can easily implement this kind of XOR logic, and you can see here, that H1 is basically, we put a sigmoid here because of this 0 1 kind of thing, that logic, or whatever the way we have implemented AND gate or gate NOT gate in the last lecture, that is basically same. So we use the sigmoid and nonlinearity, and we can essentially implement this H1 as a sigmoid of 1 minus x1 with naught of x1 plus x2, and H2 is equal to a sigmoid of x1 plus naught of x2, and y is equal to H1 or H2. So we can get. So what we can understand? A multi-layer perceptron with this virtue of this extra layer in between this input layer and output layer, with the proper weights, this kind of proper weight to input weight in the way we have understood in the last class, can predict the output of the solvers. So what we, the takeaway message is this, that is the strength of this extra layer or hidden layer. So what we have seen, in case of multi-layer perceptron, there is one or more than one hidden layers in between input layer and output layers, and the power of multi-layer perceptron is essentially coming from these hidden layers, and that is what we have to understand. Now what is happening, the neurons of first hidden layer is basically generate the multiple hyperplanes, okay, that effectively dividing the input space into many half spaces. What does this mean? Now please see this diagram. Here what we understand, that these are the first hidden layer. It is essentially is a linear separator. You can see this data distribution is basically separated by a linear. Here it is a straight line, since it is a two-dimensional. This is one neuron, this is another neuron, and this is another separator, but it's a linear separator. Here another separator, but still is linear. This is the separator. All are linear, but this is linear. But let's say it is a output layer. Now if we adjoin, if we combine these three linear separator, we can get some sort of, this separator is not linear, you can see some sort of polygon type separator. That is exactly what we are trying to understand here, that neurons in the first hidden layer generate multiple hyperplanes, we can say the linear hyperplanes, effectively dividing the input space in many halves, and the subsequent layers, maybe output layer in our case, combine these half spaces. So essentially we are combining this to get a more complicated separator. That exactly is happening. So the intersection of these half spaces from, say, convex polygons, okay, and it's called polytopes and convex regions. Okay, so this is the major power of the multiple layers, and you can see this is the only one layer and one output layer. If we increase more and more layers, okay, the more and more complex regions. So output layer then forms a uniform of these convex regions to create the arbitrarily shaped or potentially non-convex or disjoint decision boundaries. So that exactly what we have seen here. It's a very simplistic case to understand, to visualize the power of this particular hidden layer. So if we adjoin, sometimes it's called the piecewise linear decision boundaries, because any curve can be approximated by the straight lines. It is a bit simplistically, but we can say in that way. So to the ability to create a complex piecewise linear decision boundaries is the why MLP is considered the universal approach. Okay, we'll see later MLP with two hidden layer theoretically model any kind of problems, but it is not that much practical, but it is theoretically possible. So approximate any continuous function with sufficient hidden units and appropriate activation functions. So that what we have understood, that is the essentiality, or that is the importance of the hidden layers in case of multi-layer person. Even when we go to the deeper structure, when you introduce the deep learning, Then also we will come more detail about this hiddenness, how actually, but it essentially do this. Okay, so here we have seen that how this kind of hidden layer to improve or increase the expressiveness. That expressiveness will come later. How make it more powerful model, you can say. Okay. Okay. Now we are going to understand the basic architecture of multi-layer perceptron. Now, as we seen before, that multi-layer perceptrons have a more than one or more than one hidden layer between input and output layers. For example, in this case, we have a k number of hidden layers. So there is one input layer and this is an output layer. So here hidden layers with L number of this hidden layer we have a L number of neurons. So all the hidden layer may not be necessarily have the same number of neurons. For example, this hidden layer is have M number of neurons. That is the this is basically kth hidden layer. And in this way these are the connection. In this particular example, you can see there is a from x0 to all these connections are there, but it may not always the case. It is not necessarily that from input to every neuron. Okay, so there is a connection based on the particular applications. Another thing, if you say two consecutive, let's say for just for understanding, these two are two consecutive layers. So from layer 1 to layer, let's say k is equal to 2 or something, the next layer. So ith neuron to jth neuron of the next layer, the corresponding weight is W of ij. So this weight is associated with this item, and so on in the output layer. So what we have seen that the multi-layer perceptron essentially has three types of layer. One is input layer. There is no neurons is involved. That inputs are directly copied to the next layer. So inputs are fed to the network directly. That's basically the inputs are copied to the next hidden layer. And this hidden layer basically trying to help to model the this particular perceptron or multi-layer perceptron to model this not linearly separable data. So hidden layers help to model data points that are not linearly separable. So for example, we can say every Boolean function can be realized by a network with single hidden layer, that we have seen before. So then every bounded continuous function can be approximated with arbitrary small error by a network with one hidden layer. So with single hidden layer, we can any Boolean function we can implement or a bounded continuous function. With two hidden layer, that any function can be approximated with to an arbitrary accuracy. Okay, but this is not, this is theoretically, you can say theoretically it is possible, but practically there is a bit complicated. Now from the output layer, the similar, this is also another hidden layer kind of, but it is the output that it will give the output, and this is the last layer to produce the output. So we can see that here three types of layer. One is the input layer, in between hidden layers, and output. Now this is the most important thing. One is the activation function. Now activation function basically impose the non-linearity to the neurons. Now why non-linearity is required? That if we use the linear activation functions, that like this, that x equal to fx, then of all hidden units in the network, the resultant network become an equivalent network without hidden units. That means that it is just a network with one non-linear activation. So it happens because the composition of successive linear transformation itself a linear transformation. So it basically, if you compose this all this linear transformation, this becomes a single linear transformation. So the basic essence of multiple hidden layers actually will lost. So that's why we have to use the nonlinear activation function. So in about the nonlinear activation function, we sigmoid that we already known before, that this logistic function that we have seen that this is the sigmoidal nonlinearity 1 by 1 plus e to the power minus z. So this is differentiable function, and but it has a prone to vanishing gradient. So we'll come what is the vanishing gradient problem in next course study. Do you understand what actually happened due to? So for a very brief saying or briefly define the vanishing gradient, in backpropagation we are keep on differentiating our error gradient or error term. So if we keep on differentiating the error term during this backpropagation, then this error gradient becoming very small, and that's why it's a vanishing gradient. And if it is very small, then the weight upgradation algorithms or weight upgradation procedure become meaningless for the mostly for the initial layers. So that's why I called it's prone to the sigmoidal activation function prone to the vanishing gradient problem. So next is the hyperbolic tangent, is tanh function. That is basically a shifted version of, you can see it is on this 0.5, and if it is good by this 0 0, so then it will call the tanh function. Okay, so version of sigmoid function, it is also differentiable, but it also have a vanishing gradient issue. Now next thing is rectified linear unity. So it is popularly known as ReLU function. It is less computationally expensive than sigmoid or tanh, but uses that it is die for the negative input, because if a negative input means when it is less than 0, it will just 0. But there is no gradient saturation for positive input. So if you positive input, this is not having this vanishing gradient problem. And another most frequently used is leaky ReLU. It is variant of ReLU and solve this dying gradient problem of the ReLU. In that sense, it is useful. For output layer, we often see there is softmax activation function. In final layer, means output layer neural network, we saw that there is a from this raw score, output score, like this. This is maybe the output score. We put it in this kind of activation. It is equal to z I by some eta is equal to y to k, it is equal to z of I. And actually, what happened that these raw outputs, that by this softmax activation function, it normalized between values or range of values of 0, 1, 1. So what we're going to do this, if we do this and if we put this nonlinear activation, that means softmax activation over that, so this will come up like this. So it is between 0 and 1, and if you sum it up, you can get 1. So it basically kind of interpretable as a probability. And you can see that this is the highest value, and here the highest value is this. So in the multi-class problem, if you find that which particular this thing input is at the highest probability, so it has probability, so it's class 2. Okay, so something like that. So it works for multi-class classification where a single class must be chosen. So this is the basic idea of the softmax classification or softmax activation function, which is generally used in the final layer of neural network. This. Okay, now we formally define that multi-layer perceptron. So we have seen that what is single layer perceptron, there is no hidden layer, only input layer and output layer. And then our multi-layer perceptron with single hidden layer, like this, between input layer and the output layer, there is one hidden layer. And there is possible that more than one hidden layer. In this example, 2 hidden layers, but it is possible that multiple hidden layer in between input and output connection. And what we have understood that this in MLP, this hidden layer is going to improve or increase the expressiveness of the model. So in a very simplistic way, we can say that the model become more powerful, or it can model more complex problems. Okay, so this is the very basic architectures of the different MLPs with single and multiple hidden layers. Now what we have to understand that input layer output layer and hidden layer. These three type of layers is in this neural network, and we call it feed forward neural network. Why this name? I'll come next. But before that, again we have to understand what actually these layers are doing. Now, for this particular example, you can see that these are the input layers. So it is a x1 to xn input, and let's say for understanding this is the bias term or something x0. Okay, and here there is a total k number of hidden layers. Okay, 1 to k number of so 1 to k number of hidden layers, and each layer, just for first layer, has L number of neurons, and this kth layer may be m number of neurons. So the hidden layer may not have the same number of neurons. Okay, and this is the output layer. Output may be 1, output may be 2, output may be. So this is the more or less the architectural, very, you can say the very naive architectural description of this neural network, or we can say multi-layer perceptron. Now one by one we have to understand input layers basically copy the input to the next layer. There is no activation function, no summation kind of things involved. It just is copying this function to the hidden layer. So it's just input to the hidden layer, first hidden layer. Now the last layer it's produced, this is the output layer, this produce the output, and it use, but this output layer use the activation function. Now come what is the hidden layer doing. Now that is very important statement, that it learns input patterns in different layer of abstraction. As we have seen before that hidden layer, first hidden layers are basically model the very primitive geometrical patterns like just edge or slanted edge. When we going to the from input to the output direction or deeper, so these deeper layers are going to model more complex patterns. So we can say the initial layer model primitive patterns, and later layers or deeper layers model complex pattern. So that these statements are very important, that we are going to understand in detail in this course, mainly in the deep learning part. Okay. Now why it is called feed forward? Now one, the feed forward from the direction. This data is basically flow from input to output direction, from input to output direction. So that is the feed forward direction, means that the input to output direction. So in this network, the output neuron of layer, let's say this layer, a layer L become the input units to the layer L plus 1 in the. So if we assume these are two successive layers, so the output of this layer is fed to the next layer. Okay, so the L become input to the units of the L plus 1. Okay, similarly the output of L plus 1 neurons become the input to the L plus 2. So L1, L plus 2, L plus 3, L plus 4, and so on. It is increasing layers. So coefficients are flowing from input to output in forward direction. Thus, so what we can understand, that this feed forward neural network, the data or inputs are going from input to the output directions, and there is no cross connection between the units in the same layer. There is no connection from this neuron to this neuron or this neuron to this neuron. As of now, there is no cross connection, and there is also no backward connection. Also from here to here, there is no backward connection as per whatever architecture we are. And in case of, if there is a fully connected network, that every neuron from the previous layer has, you can see here, from here to here, here to here, and here to here. So all are connected. If this is the thing, from a neuron from a previous layer connected to the all the neurons of the next layer, then we can say it's a fully connected network. And it is basically for every layer. Let's look at the fully connected layer. So all neurons in the layer L provide input to all neurons for layer L plus 1. Okay. Now we have to understand that what are the actual inputs are being converted in between layers. Now we can see what is the computation in the hidden layer? So there is basically two computation. One is the summation and another is activation. So here before activation, this AX is basically is being formed, and this is the basically you can see here that B1, this is one is base bias term, plus this is the weight vector into the inputs, is input vector. So this is in metric formulation. If we write in the algebraic formulation, so we can say x of I bi1 and for summation j2 wij I1 xj. So these are this is basically the formulation of the inputs to the in corresponding hidden layer. Okay. So here we start with a MLP with single hidden layer. Now here we can see in this structure, this is input layer x1, x2 to up to xn, and this is basically the bias term. Now when we are computed that in hidden layer computation or hidden layer values, first there is some summation thing. So summation is basically done that this is the bias term. So bias coming from here, so that is B1, so from it's basically this, and then it is Wix. Now you can see Wi, Wi, W1 because this is a first hidden layer and there is a single hidden layer, so it's only first layer. So this is this W or these weights are associated with this layer, and this is the input vector. So these are the input vector. Okay, and if you see the corresponding the algebraic meaning of these metric formulations, that you can say A of xi. So that particular this for a particular neuron here or here, and this is the bias term, and this is the corresponding W I of j. I of j means from this neuron to and into jth neuron. Here both are I, so that's I, but it is from I to j is I j, and to this one means this there, and x means this particular the particular input. So it is from all the units, so it is j maybe 1, or if it is a fully connected network j2 1 to n something. So this is the basic formulations. Now after we getting this AX value, we put a nonlinearity. If we put a sigmoidal, so this G is basically a sigmoidal nonlinearity over this AX to get the output from this hidden layer. So now this HX is basically the output from this. Okay. So here the output of this hidden layer is HX. Now this HX is fed to the, since it is a single hidden layer, so MLP with single hidden layer, only one layer is there, so it is fed directly to the output. In output there is also weight and bias. Since it is a second layer, say because it is only one hidden layer, so this W, that's why W2 into this X, this H is there, and then this bias terms. So this is the thing that all neurons of this hidden layer is basically weighted to this W2. That means the weight of this output layer, and it is fed to sum it up, and then there is the non-linearity is put on this summation. So is the output activation function, but output non-linearity we are imposing, and then we get back the output coming from this. So that is the FX. So this is the formulations of a MLP with single hidden layer. Now come the MLP with multiple hidden layers. So how we calculate? The basic formulation is same, only there is a more than one. So let this MLP has a k number of hidden layers. Okay, k number of hidden layers. P is the layer index, so P is equal to 1, 2 up to k. Yeah, and H0x, this is at input level, it is just copying, so that's why it is. So what is the pre-activation? That means before activation, what are the basic formulation in these neurons? that is AP, this is the layer index, X is equal to bias of this particular layer index PHP1X. So one thing is very interesting here, that this H is coming from the previous hidden layer, okay, HP minus 1X. So that is very important, but this weight is particular for this layer. That's exactly what we have seen in the single hidden layer. Okay, so this is the layer pre-activation, and when we get this a P of X of that means this AX of in P layer, we put a activation. If we put sigmoidal, we can, if we put Rayleigh, whatever we put here, we get H. And in output layer, exactly the similar thing is happened. This activation is for output layer activation is equal to K plus 1 now, because here up to here it is a K layer, and this is P plus 1, K plus 1 layer. So here you can say H of K plus 1. So this is the basic output, you can say that this is O. O is activation function, the output layer, K plus 1X. So this is the basically UFX. So that is the output of this in particular node. So I'm going to get. So here MLP with the different with the multiple layers. Okay, so we have to understand that what is the strength of the multi-layer perceptron over the single layer perceptron. So what it is called the expressiveness of the model. So if we can say multi-layer perceptron is more powerful than single layer perceptron, we can say the expressiveness of the multi-layer perceptron is more than single layer. Now first we see the what is the expressiveness of the single layer perceptron. As you know, single layer perceptron has no hidden layer. So single layer perceptron can model only linearly separable problems. They can model and or not, but you cannot model the ZOR. That we have seen there. This is a linearly separable problem that a SLP can handle, but this is the ZOR problem. Since it is not linearly separable, SLP cannot handle. We know this very well. Now we have to deep dive that why it is so. So first of all, you understand what is the bias that is basically doing here. That question is always there is a weight, there's a bias parameters is there. Now this bias is basically change the position of the reef. So here this is basically a you can see the separator. This separator is basically what? It is a plane. Okay, this is a plane. Now if this bias term is used, that this basically the change position of the reef. So there is a position. This thing you can much more easily visualize. This, for example, in this is a straight line equation, but this is y is equal to mx. So c is not there. So c is 0. So this line is basically linked to this 0, 0 position. Now if we put some bias kind of say here, c is equal to something like bias, and this is, you can say h is equal to wx plus b. So this is, if you put some bias here, other things are same. Now you just, that is the shift, the position of the reef. So here the position of the straight line, just put it here. So this is exactly the bias is doing here, and that is very much important to understand that bias for this kind of understanding the expressiveness of these models. Okay. Now here you can see that the expressiveness with single hidden layer. So it is a multi-layer perceptron but with single hidden layer. You can see here it is a single hidden layer. So here from input this is the hidden layer. Now you can say depend on this bias kind of thing. So there is some sort of this, and if you adjoin these two in your output layer, you can get, this is, you cannot get from a single layer perceptron. So here it is the strength of multi-layer perceptron. Even it is a single hidden layer, it has, this is a complicated decision, we can say decision boundary or decision plane. Okay, so this is basically is going to improve the expressiveness or increase the expressiveness of the MLP. And here also you can say this is also single layer, but number of neurons is high. It's a 2 neurons, but it's a 4 neurons in this layer. So you can see that that this kind of thing is that much complicated decision surface. Okay, so that is very interesting, that how it is basically how the expressiveness is being increased. Not only in a single hidden layer, this is even it's a single hidden layer, but with more number of neurons, we get a more complicated or more complex model, come to model. So one, we can understand that what is the with respect to the expressiveness, the single layer perceptron with no hidden layer model only linearly separable problem. It model AND or NOT gate, but not the XOR gate. A neural with single hidden layer, though this is called one universal approximation theorem, 1991. So every bounded continuous function can be approximated with arbitrary precision by a single layer. So this will be a kind of theorem. So it is number of hidden units that is exponential in the number of inputs. So that may be possible. How many hidden units, the neurons in this hidden layer? That also, this doesn't mean that we can easily learn the parameters. So two things is not been here anything, the how many neurons in this hidden layer, and one is the convergence of this. So but it theoretically can be possible. And in neural network with two hidden layer, it is universal approximator kind of. So any function can be approximated arbitrarily accuracy by network two hidden layer. We already said that this is theoretically true, but these two things is coming. How many neurons in layers in, and what is the convergence that we cannot ensure. So here is some diagrammatic viewpoint taking this is a very well-known slide taken from this source. Single hidden layer, it is only, you can see this is single, just a straight line kind of. So half plane bounded by hyperplane kind of thing. So here also, if even this is the groupings, is all we can only this kind of region separator. If two layer, we can go for this. You can see from XOR problem we know very well. Here we can with this kind of polygonal decision solution boundaries. And if you get 3 layer kind of 2 layer arbitrary complexity of limited complexity limited by the number of nodes, we can go for any kind of this. You can say that for the very complex kind of we can get. So with this we can understand what are the expressiveness of this. Now we'll just take that and look what are the application areas of it. It's said in earlier also that application area is huge. So I put some names, some areas of very important, but it's not limited to that. You know, weather forecast, agriculture, insurance, industry, and IoT, healthcare, finance, sports, urban. So everywhere this MLP become very much prominent nowadays. Lot of application, subdomain, domain, subdomains are basically coming under this multi-layer perceptron. Okay, so to summary, in this lecture we define MLP and different component of multi-layer perceptron. Then we understand what we mean by activation function. Then we define the feed-forward neural network, that is a multi-layer perceptron, and how it to model some problems, and expressiveness of the multi-layer perceptron, that is most important. And we end with an application. In the next part, in part 3, we basically going to focus on how this MLP is being trained. Okay, only the back propagation. Thank you.